What's up? I'm Vin, and today I want to take a look at a Star Wars calculus optimization problem. Now, I'm a big fan of Star Wars, so if you are a fan as well, let me know in the comments section. What is your favorite Star Wars movie or show, starting all the way back to 1977 when the first movie came out? All right, so let's jump into this. We have Lars's moisture farm on Tatooine. There are 24 moisture processors. They have an average yield per processor of 300 cubits of moisture. And then we're told that research is conducted at the university, and it concluded that when an additional processor is used, the average yield per processor is reduced by 5 cubits. Now here comes the actual question. We have to help Owen and Beru Lars find the number of moisture processors that will maximize the number of cubits. So the main phrase here to look at is we want to maximize the number of cubits of moisture. So that's our task. And for this question, I'll be honest, what I struggled with big time was just understanding what's actually happening in this question. Like, how do I even set this up? And what helped me get started was I looked at the number of processors, and then I called the number of processors P, and Y was the average yield per processor. So if we look at this here, P equals 24. When we had 24 processors, there was an average yield per processor of 300 cubits of moisture. But then we were told that every time an additional processor is used, so let's say that I have 25 processors, the average yield is reduced by 5. So this brings it down to 295. So now if I have 25 processors, I'm going to get 295 cubits of moisture for each processor. And if I went one more to 26, this would bring the average yield down to 290 cubits per processor. So if you think about this very carefully, this is a linear relationship between P, the number of processors, and Y, the average yield per processor. So then what you could do is write an equation that connects P and Y. So what we could do is find the slope between these 2 points here, if I use the first two. And for my P values here, when they go up 1, my Y values are going down 5. So we could see this constant rate of change here. Now, another way you could find this is just find the slope between any 2 points. You could do 300 minus 295 divided by 24 minus 25. And this tells you the slope is -5, which makes sense when we reread this sentence here, that the average yield is reduced by 5 cubits for each additional processor used. So now what we're going to do is I take, let's say, the point 24, 300. And this is P and this is Y. I'm going to write the equation of a line with slope -5 through this point. So we would have -5 times P minus 24, and we have Y minus 300 equals. So if I solve this for Y, I have -5P, -5 times -24 is plus 120, and we've got Y minus 300. So to solve for Y, just add 300, and we've got -5P plus 420. So this equation here is a very important piece of the puzzle. This is going to help us answer this question at the end. But remember, don't lose sight of the actual question. The actual question is to maximize the number of cubits. So what we need to be able to do is come up with an equation, C equals, that models the number of cubits. Well, let's think about P represents the number of processors. So this is our processors here. And Y represents the average yield per processor. So this is essentially going to tell us cubits of moisture per processor. So you could see the reason why we're multiplying these two together is because when I multiply processors by cubits per processor, these units cancel out and I just have the number of cubits and I have cubits on the right. So that's why this equation makes sense. But the main challenge with optimization problems is you have to set up an equation, but you have to turn it into a single variable function. So notice on the right hand side I have P and Y, but I only want it to be one variable. So what I'm going to do is instead of saying P times Y, I'm going to replace Y with this equation here. So now I could say my function C of P is equal to P times Y, where Y is equal to -5P plus 420. And I could specify a domain here. This only makes sense if we say P is greater than 0, because if P is the number of processors, they're not going to have no processors or negative processors. They're actually trying to get moisture out of their moisture farm. So now we go forward with this. The goal is to maximize this function. We want to find what is the number of processors P that makes C of P, the number of cubits, as big as possible. So what we're going to do is we could just distribute here first. We have -5P squared plus 420P. And now just to use some of my old math to help me make sense of this. When I see negative 5p squared plus 420p, what I'm thinking of here is a quadratic that's opening downwards. So this is definitely going to have an absolute maximum, and this is going to occur at the vertex. So I could just go ahead and find the vertex here, but I'll go ahead and use calculus to find the p-value that we need. So here, to find the maximum value, I'm looking for when is the slope equal to 0. So I take the derivative to find the slope, and I have negative 10p plus 420. And now what we want to find is, we're looking for c prime of p is equal to 0 when the equation negative 10p plus 420 is equal to 0. And this is going to be true when 10p is equal to 420 or when p is equal to 42. So I could say this is our solution. If we use 42 processors, this is going to maximize the cubits of moisture that we get out of the moisture farm. But depending on how much work you have to show, sometimes you need to go the extra step and actually verify that. How do we know p equals 42 is the site of the absolute maximum? So this is where I'll just go the extra step and go forward with the verification. So to verify this, what we could do is make a sign chart for c prime. So c prime of p, the domain was, once again, p is greater than 0. And the only critical point that we had, notice this is telling us the site of our critical point. So we have a critical point at p equals 42. So if I were to plug in something like 1, that's on the interval from 0 to 42, to the derivative of negative 10 times 1 plus 420 gives me something positive. And if I plug in something greater than 42, like 50, I would have negative 500 plus 420 comes out negative. So that tells me my function c of p is increasing from 0 to 42 and decreasing for all values after 42. So that's how I know this is going to be the absolute maximum, because there's a very helpful theorem that says if a function has only one critical point, and that critical point is a local maximum, then it's also the absolute maximum. So that's what we're going to say here to help us justify our answer. Okay, so just to reiterate once again, this explanation is only going to be valid here because we had only one critical point for c of p. The only critical point occurred at p equals 42. And since we have a local maximum here, it's also the absolute maximum because it was the only critical point. So this is the justification here, but just know that this value here, p equals 42, is the solution that Owen and Beru Lars should use 42 processors to maximize their cubits of moisture. Okay, well, this is going to conclude this Star Wars problem. If you found this video to be helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comments section below. And thanks for watching.